Welcome to this explainer. Today, we're diving straight into what is literally the ultimate high-stakes balancing act in all of science and engineering, the physics of a nuclear reactor. We're going to look at the exact mechanics of how we keep one of the most powerful forces in the universe perfectly and safely in check.
So, how do you control a nuclear chain reaction? That's the central puzzle, right? How exactly do engineers harness all this chaotic atomic energy without it just fizzling out into nothing or, well, violently exploding? It's this absolutely fascinating puzzle of geometry, materials, and some seriously relentless math.
The absolute baseline goal of any fission reactor is actually pretty simple. It needs to produce a continuous, feasible level of power that is, and I'm coding here, capable of being controlled at will and safe to operate. Sounds entirely reasonable, doesn't it? But achieving that serene, steady state at the atomic level, man, that requires a microscopic balancing act of epic proportions.
All of this energy production happens right here in the core. Now keep in mind, the core isn't just some solid block of glowing green metal like you see in the movies. Actually, scratch that. It's a highly specific, carefully engineered mixture. It combines fissile material, the stuff that actually splits, along with fertile material and other non-fissionable elements. Nailing this exact mixture is step one in taming the reaction.
To really understand how this core works, we kind of need to put on our accountant hats. We are managing a neutron economy, and in this ledger, our budget absolutely must balance perfectly. Think of it like this. On the income side, we've got neutron production. Those are the new neutrons born from fission. But then we have our expenses, our neutron loss. This happens in two ways. Either they're absorbed by heavy nuclei without causing a fission, or there's leakage, where neutrons simply fly right out of the core. If expenses exceed income, the whole thing shuts down. But if income exceeds expenses, well, hold that thought. We'll get to that in a bit.
So the absolute crucial point here is achieving what physicists call criticality. This is the magic number. Criticality is the state where our net growth rate, which we call the multiplication factor, or K, equals exactly 1. K equals 1. It literally means for every single neutron we lose to absorption or leakage, exactly one new neutron is produced to take its place. Just a perfect, unending cycle.
When you look at the math of this balance, it's actually surprisingly straightforward. These formulas are really just mathematical ways of dividing our total neutron production rate by our absorption and leakage rates. It's just income divided by expenses. If the top matches the bottom, boom, K equals 1.
Now, there's a really interesting contrast here between the theoretical and the practical. You see, to make the math a little easier initially, physicists dream up this infinite core, which they call K infinity. In an infinitely large reactor, no neutrons can ever escape, so your leakage is just zero. But obviously that's a fictitious model. In the real world, we deal with the effective core, or KF. Because a real reactor has actual boundaries, neutrons are absolutely going to leak out. And how many of them leak out depends entirely on the physical size and shape of the core itself. Because those neutrons are leaking from the surface, engineers have to calculate the exact critical volume and its corresponding critical mass. They have to find the perfect physical size and geometry of the fuel mixture to ensure that leakage and absorption are perfectly offset by production. That's how they hit that pristine KF equals 1 balance.
To give you a real tactile sense of scale for what these calculations actually look like, imagine this. If you wanted to build a perfectly spherical reactor core using pure uranium-235, the critical mass you'd need to hit KF equals 1 weighs about 50 kilograms.
But watch what happens if you change the material. The math shifts completely. If you swap that out and use pure plutonium-239 instead, your critical mass shrinks right down to just 10 kilograms for a sphere. Because plutonium has a different atomic cross-section, basically meaning it's way more likely to interact with a neutron, its absorption and fission rates change everything, giving you a totally different critical mass.
And this leads us to an absolutely ingenious engineering trick. Nuclear fuel is incredibly expensive and super complex to produce. So to maximize fuel economy, engineers surround the core with materials called reflectors. These basically act like mirrors for neutrons. Instead of those neutrons leaking out and becoming a lost expense on our ledger, the reflector bounces them right back into the active core. It's so clever, it reduces your overall leakage rate, meaning you can hit criticality with a smaller size and a lot less fuel.
Okay, so we've seen how perfectly balanced a critical reactor has to be, and the tricks we use to maintain it. But what happens if that balance fails?
What actually happens to our neutron economy if a reactor goes supercritical and that multiplication factor K tips to be greater than 1?
The source text walks us through this with a terrifyingly fast hypothetical scenario. We're going to calculate what happens over the course of just a single second if every single neutron released causes another fission, assuming a generation time of exactly 0.1 seconds.
Let's break down the mechanics of this disaster step by step. Step 1, we assume total efficiency. Every single neutron causes fission, meaning capture and leakage are 0. Step 2, we know the average number of new neutrons produced per fission is 2.5. Step 3, that means our multiplication factor K jumps to 2.5, so every generation is 2.5 times larger than the last one. And finally, step 4, we apply the exponential growth formula given in the text over a time frame of just 1 single second.
When you plug those numbers in, wow, the result is absolutely staggering. In just 1 single second, the original number of neutrons in the reactor multiplies by more than 3 million times. As the text starkly points out, the system is highly supercritical and goes entirely out of control. This result really shows why keeping that multiplication factor in check is a matter of absolute, uncompromising safety. An unbalanced nuclear reactor doesn't just slowly overheat over a few hours. If K jumps significantly above 1, it violently runs away from you, literally in an instant.
And get this, there is a final, really surprising fact hidden in the text. You know that 0.1 second generation time we just used? That actually includes a natural speed bump called delayed neutrons. The text points out that if we didn't have those delayed neutrons slowing the whole process down, the generation time would be less than a millisecond. So that 3 million times multiplication, it wouldn't happen in a second. It would happen in a fraction of the blink of an eye, generating a number so massive it's practically forbidden by the math.
So I'll leave you with this to ponder. We just saw how fast this microscopic neutron economy can go completely catastrophically bankrupt. Given that atomic physics naturally wants to race towards uncontrollable exponential chaos in mere milliseconds, just how fundamentally perfect must our human engineering be to harness the power of the stars, keep it perfectly balanced at K equals 1, and do it safely right here on Earth? Thanks for joining me on this explainer, and keep questioning the science around you.